Right, so pictured below are 5 typical force diagrams for an object that is moving vertically. There could be a third force or a fourth force, but usually there's just 2 or even just 1 for us to think about. The key thing or the key reason why we draw force diagrams is it helps us understand or visualize how the net force relates to the velocity. So if the net force points in the same direction as the velocity of the object, then we know the object's going to be accelerating the way we normally think about the word accelerate. It's going to be speeding up. But if instead our velocity points in the opposite direction of the net force, then that net force causes the object's motion to slow down. And so we want to use these diagrams to help us see that, how if the object, say, was moving up in this case, if that's the upward direction is the motion, we usually would call that the positive direction. And so we would write our sigma f as F1 minus F2. But if instead our object was moving down, if it was falling, then we would usually call that our positive direction. At least that's the way that I teach it, or I do it. And so in this case, I would set up my equation as F2 minus F1. So my suggestion to you, and it's not the only way of doing these problems, but you always let the picture determine the way that you subtract forces or the way you add forces. So choose the positive direction as the direction of motion. This object, if it were moving up, still I would take F1 minus F2 equal to ma. What the difference would be here is because it has a greater force downward than upwards, it would be losing speed. And so my F1 is less than F2, so this side of the equation would end up being negative, and my acceleration would be negative. So it tends to work out that way. And if the forces are the same, then your acceleration is 0. That could mean that the object isn't moving, but it could also mean that the object moves at a constant speed. So again, force diagrams help us visualize how the motion will change. All right, so these are the 5 forces that we mainly focus on in this class. Once in a while there'll be something unusual, but these are the 5 you want to make sure you understand. And notice that I've listed off the most common symbols that are used for each of the forces. You can use any of those symbols or something similar to them, but definitely pick something that other people would recognize. The most common way to do this is with a capital F for force and then a subscript that indicates what type of force it is. When we're drawing a force diagram, we want to make sure that we use a dot to represent the object, and then arrows going from the dot to represent the various forces. So do not do something like this. Even if it's somebody like pushing on something, don't draw your arrows like this. Okay, always they always look like they're pulling. They're always pointed away from the dot. And no need to draw a picture or anything of the object. You can just work with a dot or maybe a small box. That's the easiest to work with. So applied forces, those are forces where it's something from the outside, maybe somebody pushing or an engine pushing on something. That's what an applied force is. It's actually sort of any force that doesn't fit all the rest of the categories. Tension is usually reserved for a situation where there's a rope or a chain, something that is pulling on something that is kind of slack unless you are pulling, so it needs that tightness to it. That's your tension force. The gravitational force is also known as weight. Make sure that you recognize that within your problem solving. And again, you can just label that F sub g for gravity, but I tend to label that force mg right away because I almost always have to calculate that. Recall that the value of g is approximately 9.8 here in Champaign, and you can certainly use that number if you like, but you're going to see me use 10 in my problem solving and on tests and so forth. There's no need to be that accurate when we're just practicing a skill. But if you're working with a lab situation, you're trying to measure up to a certain value, then you want to use that 9.8 value instead. Normal force and friction we will talk more about in the next section, but just recall that a normal force is always perpendicular to a surface. So on a flat surface, which is what we are normally dealing with, your normal force will point up. But as we'll see very quickly, that's not the only situation. We're gonna see other situations as we go. So if you have an incline, then your normal force is going to point perpendicular to that. So that's really the key. And then frictional forces, for the most part, point against the object's motion, although there are some strange counterexamples to that we will talk about throughout the year. But for right now, you can stick with friction opposing the motion, pointing opposite to the direction that the object's velocity points. All right, so let's take a look at a couple of examples here. So a rocket just after launch, and again, we're just working with vertical motion at this point. So the rocket will be a dot. There would always be weight pointing downward. I like to just label that mg right away. Usually I'm going to have to calculate it from a mass. And then if it's just after launch, there must be a bigger upward force than a downward force. And we would probably classify that as an applied force. If I have an elevator that's coming to a stop at ground level, so it's coming to a stop and its motion is downward, so I would be thinking about down as my positive direction. There must be less force down than up if the object is coming to a stop, if it's slowing down. And so the weight is still going to be down here, but some sort of upward force. In this case, since it's an elevator, I'd probably think of it as a tension force or a cable. It's possible that there's some friction, but the problem doesn't really specifically mention it, so I would not include it in my picture. If I have a person in an elevator that's heading down from the top floor, they must be beginning to accelerate from that top floor, so there must be more force down than up. Again, I have weight pointing down, and since it's a person in an elevator, the upward force on that person would be the normal force, a force of a surface on the object. A ball held by a person at constant speed, very important phrase. I usually circle it as I'm working to make sure I don't forget. That indicates that the forces must balance. So I'm going to try to draw those forces to be the same length. I might even mark them like this with congruent marks to indicate that they truly are equal to each other. Again, vertical forces I'm working with, so I'm going to have that weight force down. And then since this ball is being held, I could call that an applied force, or if you wanted to call it a normal force, you could. A ball that's up in the air, meaning it's not being thrown, it's not being pushed or pulled or anything, only has the gravitational force on it. And since it's ideal in this situation, we're not going to worry about air resistance or air drag. But if I have a skydiver that's in free fall, there's going to be that downward force, the person's weight, and then there's going to be some sort of a drag force against it. Again, you'll have some sort of indication when you should include that drag force, some indication that it's a realistic problem or the drag force will be specifically mentioned.